You ready?
Yes.
All right, cool. So it's our pleasure today to have Emily Nardoni to give our seminar from UCLA. And she's going to be talking about SUN Seiberg-Witten theory and its relation to adjoint QCD.
Thank you. Thank you for having me. So yes, today I'm going to tell you about what you can learn about adjoint QCD from Seiberg-Witten theory. And this is work that is done with my collaborators from UCLA, Eric Doker, Thomas Dimitrescu, and Efra Gershkovitz. And our paper should be out soon. Okay, so an old and interesting problem is how to probe the low energy structure of gauge theories at strong coupling. So this is hard. This could be hard with SUSY. This is especially difficult in non-supersymmetric theories where I have less tools at my disposal. So today I'm going to be interested in probing this question in the context of adjoint QCD, by which I mean the 4D gauge theory with SUN gauge group and generally NF massless Weyl fermions that transform in the adjoint representation of the SUN gauge group. So here, this little I is some index that runs from 1 to NF. So these, so this class of theories are asymptotically free for NF less than or equal to 5. That's the asymptotic freedom bound. And so here I'm just giving you some details of what we know about the phase structure of these theories as a function of NF. And the statement is that we know quite a lot about the special low NF cases of NF equals 0 and NF equals 1. And then the higher NF cases are much less well understood. So NF equals 0 is just pure Yang-Mills theory, and this depends on the theta angle, and it's expected to confine for all theta. NF equals 1 is supersymmetric. It's N equals 1 super Yang-Mills. And this is also very well studied. This theory is confining and gapped. In particular, there are N degenerate supersymmetric vacua that are labeled by the phase of the gaugino condensate. So I told you that the higher NF cases are much less well understood. And so in particular, the first harder case is NF equals 2. So this is the case I'm going to be focusing on for the rest of this talk. And so let me start by just giving you some background info on the NF equals 2 theory. So the NF equals 2 theory has two massless Weyl fermions in the adjoint of the gauge group. And so this little I is a doublet index of the chiral SU NF equals 2 global symmetry. There's also a classical U1, I'll call it little r symmetry, which is broken by an ABJ anomaly to a discrete Z4n subgroup. With respect to discrete symmetries, charge conjugation and time reversal are preserved. There's also a discrete one-form center symmetry, a ZN one-form center symmetry that's related to the center of the SUN gauge group and is also useful for diagnosing confinement. And furthermore, something we definitively know about these theories comes from the Vafa-Witten theorem. So in particular, for NF equals 2, the Vafa-Witten theorem tells me that the combination CT, or parity, but I'll use C and T rather than P throughout this talk, as well as a U1 subgroup of the chiral SU NF equals 2 symmetry cannot be spontaneously broken. Okay, so I told you that what we know about the low energy structure of this theory or behavior of this theory is much less well understood. However, if I make some standard assumptions about vector-like gauge theories, how those are supposed to behave at strong coupling, then this would suggest the following picture. So the suggestion for the phase of this theory at low energies is that the fermion bilinear condenses and this fermion bilinear breaks the chiral SU NF equals 2 symmetry to a U1, which is in accordance with the Vafa-Witten theorem. This fermion bilinear also breaks the discrete Z4n symmetry to a Z4 subgroup. And this phase is confining because the ZN1 form center symmetry is unbroken. Furthermore, charge conjugation and time reversal remain both unbroken in this proposed phase. So this picture of this chiral symmetry breaking pattern gives two Goldstone bosons for this breaking pattern, and these two Goldstone bosons describe a CP1 sigma model. So I'll refer to this proposed phase of NF equals 2 adjoint QCD as a CP1 phase from now on. And in particular, there are n degenerate copies of the CP1. And so these n copies, these are in accordance with the n different phases that the fermion bilinear can take. So I said there's not really much concrete evidence for this. It's mostly lore, but one important comment is that this proposed CP1 phase that I've just presented to you is economical in the sense that it doesn't require phase transitions in order to be consistent with the lower NF phase structure that I just reviewed for you. So in particular, if I add small fermion masses, then I would reproduce exactly the structure of the n equals 1 supersymmetric vacua if I integrate out one fermion with a small mass deformation. And then if I integrate out the other in the right way, then I reproduce the known structure of the NF equals 0 vacua of just pure Yang-Mills. So the question that I'd like to ask in this talk is, can we test this proposed phase of NF equals 2 adjoint QCD, or can we provide evidence for it? And so this is going to be the content of the rest of this talk, and I'll be entirely focusing on this NF equals 2 case. So from now on, when I say adjoint QCD, I mean NF equals 2 adjoint QCD. So we're going to follow the following strategy, which is following work by your colleague Cordova and Dumitrescu. And that strategy is to embed adjoint QCD into n equals 2 super Yang-Mills. So this follows from the following observation, that we can flow to SUN NF equals 2 adjoint QCD from n equals 2 super Yang-Mills by integrating out the complex vector multiplet scalar, call it phi. In particular, in this identification, the chiral SU NF equals 2 global symmetry is identified exactly with the SU2R symmetry of the n equals 2 theory, and the two Weyl fermions are identified with the two components of the gaugino of the n equals 2 theory. So this presents the following strategy, that we add the following soft supersymmetry breaking non-holomorphic mass term to the n equals 2 theory, this trace phi bar phi. And here I'm going to call the SUSY-breaking parameter m squared. So the first comment is that this very particular deformation that I've written here, it's special because trace phi bar phi is the real scalar at the bottom of the protected n equals 2 stress tensor multiplet. So in particular, this means it can be tracked to the Coulomb branch of the n equals 2 theory in the IR. So this is very important for us. And this is following work by these authors. Some more comments. So for m much less than the strong coupling scale of the n equals 2 theory, we can reliably analyze the effect of this SUSY-breaking deformation. And this is because we know the exact low energy effective description of the n equals 2 theory, Seiberg-Witten theory, and its SUN generalizations. Then for m much bigger than the strong coupling scale, we flow to adjoint QCD. So an important comment is that this deformation, it preserves all symmetries of both theories, except supersymmetry. But in particular, it preserves all other symmetries. For example, it preserved this SU2R chiral symmetry. And therefore, all anomalies are automatically matched along the flow for any value of the SUSY-breaking parameter M. And so this is important because therefore any phase that we encounter as we vary M when we do such a soft SUSY-breaking analysis is a candidate phase of adjoint QCD in the sense that it matches all symmetries and anomalies. Now, of course, the M much greater than lambda limit is uncontrolled, so I can't actually prove with this sort of analysis which phase is actually realized by adjoint QCD. But this is still a powerful tool for suggesting a possible consistent phase. So the question I would like to pose is the following, which is using this softly broken n equals 2 theory as I just described for you, can we find an effective description which qualitatively reproduces the features of this likely CP1 phase of adjoint QCD? So with all these features I reviewed for you a bit ago. So in particular, chiral symmetry breaking, confinement, the right discrete symmetries preserved, and so on. So this is a bit of a loaded question. And immediately upon asking this question, there are two difficulties that come to mind. And so the first is the following comment, that at small m, so small SUSY-breaking parameter, I told you that I could analyze this theory reliably on the Coulomb branch of the n equals 2 theory. And when I do this, the result is I get a theory in the Coulomb phase. So in particular with massless gauginos. And a Coulomb phase with massless gauginos, it's very far from the CP1 phase with confinement that I described for you earlier. So the first comment is that if I hope to realize this goal and to make contact with a CP1 phase, it will happen at larger m, because we know it happens at small m, and it's not this. And the large m limit is uncontrolled. And furthermore, it will require at least one phase transition from this Coulomb phase vacuum at small m. So that's the first comment. The second comment is that, well, the n equals 2 moduli space is very large. It's n-1 complex dimensional. And well, I need a guess as to where I should try to do this analysis of the soft SUSY-breaking analysis I described to you if I'm hoping to get out of phase with these features. So the answer that I'll argue for you is that you should do this analysis near the multi-monopole points or maximal degeneration points of Seiberg-Witten theory, and that indeed, if you do this, you can realize such a goal. And so for the rest of this talk, this is what I'm going to explain for you. So first, I'll begin by just a brief review of these multi-monopole points, and I'd like to motivate them as a starting point for our analysis. And then I'm going to do this procedure that I told you of adding the soft supersymmetry-breaking deformation to the effective Lagrangian near these points. And I will describe for you the results of a semi-classical analysis of the resulting phase structure in these effective theories. And the result that I'd like to explain for you is that we'll get a sequence of phase transitions as a function of the SUSY-breaking scale that interpolate between the supersymmetric phase at small m, which is some Coulomb phase like vacuum, and a phase with the properties of the CP1 phase at large m, which we expect might actually be realized in adjoint QCD. So this is where we're going at this point. If there are any questions before we continue, this is a good place. Okay. All right, so let's begin with just a brief review of the n equals 2 moduli space. So I'll remind you that n equals 2 SUN super-n mils has an n-1 complex dimensional moduli space of degenerate supersymmetric vacua known as the Coulomb branch. And a gauge invariant basis on this moduli space is given by the coordinates UK, by which I mean traces of powers of the complex vector multiplet scalar. So this K index runs from 2 to n. At a generic point on the Coulomb branch, the SUN gauge symmetry is broken to a U1 to the n-1. And there are n-1 abelian vector multiplets for these n-1 abelian gauge group factors. And throughout this talk, I'm going to call the scalar at the bottom of these abelian vector multiplets also phi, but it's a var phi. And then everywhere I'm going to use this little m index to index the n-1 gauge groups. So little m runs from 1 to n-1. So a discrete Z4 symmetry is generically preserved on the moduli space. And so the symmetry that acts non-trivially on the moduli space is the discrete Z4n mod this Z4, which is a Zn symmetry that acts on the moduli space. So there are singularities on the moduli space where additional particles become massless. And so when a monopole becomes massless, there is a hypermultiplet, which is charged under a U1 gauge group factor that describes the light monopole. This was understood by Seiberg and Witten. And so I'm going to call the scalar of that hypermultiplet that describes the light monopole, I'll call it H. And so H has a little I index, which indexes the SU2R symmetry because H is an SU2R doublet. Now there are n multi-monopole points or maximal degeneration points on this moduli space, which are related by this Zn symmetry I just described for you. And at each of these multi-monopole points, n-1 mutually local dyons become massless at once. So these were the points that were studied back in the 90s by Douglas and Schenker. Now, in an appropriate duality frame, one of these multi-monopole points describes the n-1 light monopoles becoming massless. And in this duality frame, the vector multiplet scalars, these are identified with the A-dual periods of Seiberg-Witten theory. And so this is the frame in which we'll work for the rest of this talk. And so I'd like to argue for you that these multi-monopole points are the right points to look at to realize this goal of getting out the properties of the CP1 phase. And so first I'd like to motivate for you why this is the case. And the first motivation is simply that this actually worked for SU2. So your colleague Clay and Thomas Dumitrescu, in their work, they showed that yes, for SU2, I can realize this goal. And so I'd like to briefly review this story in SU2 for you. So in SU2 for n equals 2, the moduli space has two strong coupling singular points, and these are the monopole and the dion points. I've just drawn them in the U plane here to remind you. And so the statement is, if I add the SUSY-breaking deformation to a generic point on the Coulomb branch, well, then the minimum of this SUSY-breaking potential sits at the origin of moduli space. And in this vacuum at the origin, I can study this vacuum. Only the scalars will get a mass. Everything else, including the gauginos, will remain. So the gauginos will remain massless, and the theory is in a Coulomb phase vacuum. Now, instead, if I add this deformation near the monopole point, of Seiberg-Witten theory, I get a different type of vacuum. So here I've written for you the potential expanded near the monopole point, including this the SUSY-breaking deformation, which remember goes like m squared. Those are these m squared terms. And so this has some important features. So first of all, the SUSY-breaking potential, it gives a positive mass to the vector multiplet scalars. It also gives a tachyonic mass to the monopole fields, the hypermultiplet scalars, which played an important role in studying the phase structure. Then there's also, I'd like to point out this tadpole term that's linear in the vector multiplet scalar. And this tadpole comes from matching onto the Coulomb branch expression when I integrate out the hypermultiplet. So in particular, I'm just going to go back for a second. So when I integrate out the hypermultiplet, I need to match this potential onto this curve. And I'm expanding near the monopole point. And at the monopole point, I'm sitting on some slope. And so that tadpole is the linear approximation to this curve at that point. Okay, so I have this potential. I can do some semi-classical analysis. And the result, I'll summarize for you as follows. So here, I'm very schematically plotting the vacuum energy of different locally stable vacuum solutions as a function of the SUSY-breaking parameter m. So in particular, at small m and stable up to some maximum value, there's a vacuum, which is the global minimum of the potential, which has the HVev set to 0. And in this vacuum, if I expand around this vacuum, I'm in a Coulomb phase. Then at some larger value of m, because of this tachyonic mass term for the monopoles, at some point at large enough m, I'm going to want to roll onto some direction of moduli space or some direction of this potential where the HVevs get where the HVevs turn on. And then I'm going to get a stable vacuum where H gets a Vev. And in such a vacuum, the magnetic photon gets a mass. And so this is interpreted as confinement from the UV perspective. And then, as I've shown here, there's going to be some transition points, call it M star, where I switch from wanting to sit in this Coulomb phase vacuum to wanting to sit in this large M vacuum with H, this confining large M vacuum. And this is a first order phase transition. You can show that these are disconnected in field space. So in this large M vacuum, since H is an SU2R doublet, remember that's what this little I index, it's an SU2R doublet index. It breaks the chiral SU2R symmetry to a U1R subgroup, which is exactly the symmetry breaking pattern of this CP1 phase. And there are 2 Goldstone bosons from the symmetry breaking pattern, which describe a CP1. So this was analysis I just described for you near the monopole point, but there's a second CP1, which comes from the dion point. And so I get 2 CP1s, which is exactly what I would have expected. So that was the story. Yeah.
Sorry, can I ask a question?
Yes.
Oh, Sav, go ahead. Sorry.
No, go ahead now.
I was going to ask if you could remind us why a magnetic photon getting a mass is confinement for the electric charge.
Right. So from this perspective of the UV theory, like the electric weak coupling variables, when the U1 gets Higgs here, it's a magnetic U1. I'm in some frame where this is magnetic from the perspective of the UV theory, and so this is the mechanism that was described in the original Seiberg-Witten theory, that this is exactly confinement. Furthermore, I mean, you can see that the center symmetry is unbroken in this phase, which is also the signal for confinement.
Right. So here you're sort of jumping from the Coulomb branch to the Higgs branch, and sort of this transition is what sort of is this phase transition from the Coulomb phase to, I guess, a CP1 phase.
That's exactly right. So the statement is that if I analyze, so I'm expanding this potential in these magnetic variables in the magnetic frame near the multi-monopole, or in this case, just the monopole point. And if I do so, then I would predict from studying the phase structure of this potential that at small m, I'm in some Coulomb phase vacuum. And then at larger m, like this potential wants to sit in a CP1 like vacuum. That's exactly right.
And so one last, I guess, silly question. When the magnetic photon gets a mass, that means you're breaking the magnetic center symmetry. Oh wait, we're in SU2. Sorry. Okay.
Yeah. Yeah. The center symmetry is preserved. Yeah.
Right. Okay. Good. All right. Cool. Thank you.
Yes. Is there another question?
I think so. Could you just explain again a little bit where the tadpole term is coming from? I mean,
yes.
Is it derived, or it's just put in to match what you expect near the origin?
Right. So, well, it's derived by matching the expression to the origin, and so that's important. Like in the sense that in order to check what this supersymmetry-breaking deformation flows to, it needs to flow to the stress tensor in the IR, and basically I can figure out what that is by figuring out what the stress tensor is in this theory near the monopole point. But then this is up to improvement terms, and the improvement terms come from matching to the exact expression for the scalar potential near once I've integrated out the hyper. So it comes from matching upon integrating out, but it's an important piece that's needed for the consistency of what this operator actually flows to in the IR. Did that answer your question?
So the connection between the perturbation you're turning on and the stress tensor requires unbroken n equal 2, right?
That's right. So n equals 2 is unbroken. Well, no. Okay.
So I'm a little confused about why that helps you to know that it came from a protected multiplet before you broke supersymmetry.
Right. It helps you at small m. So at small m, in an expansion in m over the strong coupling scale, so then the statement is, I know, like, to first order in that expansion, that this should match onto the improved stress tensor in the IR. And so strictly speaking, this is a statement which I know at small m, and so these statements about larger m are like I said before, they're uncontrolled, because this operator absolutely could get corrections.
Gotcha.
But I'm just not adding those corrections.
Okay. Thank you.
Mm-hmm. Okay, thank you. Other questions? So, okay. So this was some nice story in SU2, and the immediate lesson I learned in generalizing to what I should look at in SUN is that, well, why did this work out? Well, it worked out because I was at a singular point, and at singular points I have these hypermultiplets, and these hypermultiplets have exactly the right quantum numbers to break the chiral SU2R symmetry and to Higgs these U1 gauge group factors, which is necessary for confinement. So, okay, so that's the first statement. We need to look at singular points. However, of course, for n greater than 2, there are many additional singular points. And so why should we look at these, I'm arguing for you, these multi-monopole singular points? And so I'll give you a couple of reasons. So one is that the multi-monopole points are the unique points with n-1 massless mutually local scalars that can Higgs the whole gauge symmetry. So for example, this is not true of the Argyros-Douglas points, for example. The next point is that these multi-monopole points lie on a special slice of moduli space, which preserve already the C and the charge conjugation and time reversal symmetries. So again, these could be spontaneously broken, but at least these points lie on a slice of moduli space which have the right symmetries of adjoint QCD. The third point is proximity to the n=1 vacua in the following sense. So I know that the CP1 phase of adjoint QCD is close to the n=1 vacua in the sense that when I add small fermion mass deformations, like I briefly described for you, I match onto these n=1 vacua. Well, the multi-monopole points are also close to the n=1 vacua. They actually become the n=1 vacua upon deformation of the n=2 theory with the n=1 breaking deformation, or n=1 preserving deformation. Okay, so for the rest of this talk, I will take as my starting point for analysis the effective theory near the multi-monopole point, in particular in the duality frame where the n-1 light states are monopoles, so near one of these multi-monopole points. And I just argued for you that there are many nice motivations for doing this. However, I would also like to emphasize that there are some basic qualitative puzzles that we will need to resolve for n greater than 2. And the first basic puzzle is the fact that, well, the SUN case is basically, in some sense, n-1 copies of the SU2 case, in the sense that now there are U1 to the n-1 gauge group factors, there's n-1 vector multiplets, hypermultiplets. And so in this case, how will it be the case, like I said, I would like it to be, that all of these Higgs vevs, these monopole vevs, align to preserve a U1R symmetry. So if I want to get this chiral symmetry breaking pattern out, this seems like a very non-generic feature of such a theory. Or furthermore, a related question is, how does a single CP1 come out rather than, say, n-1 copies of a CP1? The next point is, well, so for SUN, I have all these other fields, and so I have the possibility for many more phase transitions as a function of M. And so I can ask, what is the pattern of phases and transitions? And I have the possibility for much more rich structure than the SU2 case. And furthermore, even though this multi-monopole point preserves the right discrete symmetries, well, I need to check if they're spontaneously broken by the vacua. So this is some non-trivial question that we'll need to see how this works out. So now I'd like to tell you about the results. So first, I'll give you a bit more details about this effective Lagrangian near these multi-monopole points, plus the SUSY-breaking deformation expanded near these points. And so in particular, I'm going to focus on this slide on just the scalar sector of this theory. So the fermions and the gauge fields, their interactions are completely fixed by supersymmetry. So I'm just going to give you some details on the scalar sector. So here I've written the kinetic terms in this theory. And here are the kinetic terms for the vector multiplet scalars. These have the conventional supersymmetry friendly notation, where this effective matrix of couplings is sits out in front of the kinetic terms. And so this TMN, the eigenvalues of this matrix are the couplings in the theory. And so I'm going to give you some more details on this on the next slide. And then these are the kinetic terms for the hypermultiplet scalars. So then I can write the scalar potential. And so the scalar potential has the quartic supersymmetric terms. So for example, these are the quartic in HD terms of my supersymmetric theory. This is some n=2 abelian Higgs model with some very particular scalar potential. And then there's the supersymmetry breaking deformation, which I'll give in a moment. So again, here I'm using these little m and n indices to index the n-1 U1 gauge groups. And every formula I write on any slide usually has a twiddle, and the twiddle means that I'm dropping factors of 2 and pi and so on. It's just to make the formulas look nicer on the slides. Oops. So we determine this SUSY-breaking deformation by matching. So I talked a little bit more about this in response to the question, by matching to the IR stress tensor on the Coulomb branch upon integrating out the light monopoles. And so again, this is some matching I'm doing at small m, and here I'm writing some plus dot dot dot, which are higher order corrections, which I am ignoring for now. So so I already gave you some explanation of these sorts of terms I get in the SU2 case, and I'll just point out again for this SUN case that the SUSY-breaking deformation contributes a positive mass to the vector multiplet scalars. It contributes a tachyonic mass to the monopole scalars, these hypermultiplet scalars. And then I get this tadpole term from matching to the Coulomb branch expression. Exactly the same sort of thing, situation as SU2. So then the final comment I'll make about this effective Lagrangian is that, as promised, it preserves these discrete symmetries. I said it preserves, for example, charge conjugation acts on these IR fields by permuting these gauge group indices by like little m to n minus little m on all the fields. And you can convince yourself by staring at these formulas that this is preserved because this T matrix of effective couplings also has the same symmetry. And then the other thing to check is just that this tadpole has this sign, and this sign also has the same symmetry. So this is indeed preserved as promised. So I'd like to highlight the role of this matrix of couplings in this abelian Higgs model. So these are the couplings. There's this logarithmic running factor, and then there are threshold corrections. So one thing we did is we computed these matching corrections, matching contributions, and we did it with a strong coupling expansion of the period integrals near the multi-monopole points in Seiberg-Witten theory. So just doing some hard integrals. And the results for what these matching contributions are is as follows. I've written them here. You can write them in terms of sines and cosines. That's what these S's and C's are. And so in particular, there are diagonal contributions and there are off-diagonal contributions. So this is a pure, and just to emphasize, this is a purely supersymmetric object. This is an object in the abelian Higgs model before I even think about deforming with the SUSY-breaking deformation. So I'd like to point out the important features. So the first important feature is that these off-diagonal matching contributions, these are responsible for coupling the U1, the n-1 U1 gauge group factors together. And these are very important for resolving some of the naive puzzles that I posed for you a couple slides ago. And I'll show you how that works out in a bit. Another comment is that, well, these couplings depend on the RG scale, we call it mu. So in a full quantum mechanical treatment of this model, mu defines a cutoff for my theory. Now, I'm going to be doing a semi-classical analysis. And so for the purposes of this semi-classical analysis, I'll treat mu like part of the definition of the model, kind of something I can tune. Now, with that being said, this T matrix, it appears in front of the kinetic terms. It must be positive definite. And so this sets the scale below which the effective description of the supersymmetric theory in terms of this abelian Higgs model that I wrote down is valid. And so you can check we checked by explicit computation with this matrix I wrote up there for you, that this scale, this positive definite scale, is around lambda over n squared. And so, and this actually also corresponds to the scale at which of the mass scale of the lightest W bosons in the theory. So these are the lightest massive BPS states at the multi-monopole point. And so this scale this scale of the lightest W bosons, which is actually coincides with this positive definite scale, which makes sense. So this is some cutoff on my effective description. So I'd like to just point out this cutoff, it looks small. It goes like 1 over n squared. So it goes to 0 at large n, and indeed this is very small. And so this is related to subtleties in the large n limit in this theory. And so this is something that was discussed, for example, by or originally by Douglas and Schenker back in their original paper. And so partly related to these subtleties, we have gotten no mileage out of a large n limit in this theory. So everything I tell you will be things we figured out at finite n. However, like I'm doing here, where I'm giving you how some quantity scales with n, I'll do that sometimes, and that's either to simplify a complicated expression or to test our intuition about how something you think might should scale with n. So that's just some aside on the n scaling of things. Okay. So to be very clear, this model the SUSY-breaking model I've just presented for you, it reliably describes the effect of deforming Seiberg-Witten theory only in a very strict regime of parameter space. For example, the cutoff on this theory, this lambda over n squared that I just described for you, this also defines a cutoff on my phase space, and in particular, all vevs should be less than that cutoff. For example, the vevs of the vector multiplet scalars. So that's something that's necessary for the validity of the effective supersymmetric description. Furthermore, what I told you is only valid at very small m. And this is because, for example, there are higher order and m over lambda corrections to these formulas that I wrote down for the SUSY-breaking deformation. And I put the 1 over n squared just because, since I know the 1 over n squared cutoff, that's a refinement of the fact that m should be much less than lambda. So, okay, you should ask, what actually happens when I analyze this model in this regime of parameter space? And the answer is absolutely nothing. So there are no valid semi-classical solutions to this potential that satisfy these cutoffs. And so instead, we will allow ourselves to explore beyond these strict limits, and we will perhaps blindly hope that the effective description I've just described for you will capture the phase structure in a qualitative way. So this is an example, I think, of maybe the ends justify the means a bit, where because we get answers that are sensible and we get a sensible picture, it is worthwhile to do such an extrapolation.
Sorry, how should I understand the fact that you cannot find any valid semi-classical solution? Does that mean that the theory with that particular deformation will never run into that situation at all, or there was inconsistency of setting up the analysis? Which way should I?
Right. So, like, strictly speaking, this theory cannot reliably describe the physics I want to get out. So instead, like I should think. So I've written this theory as coming from Seiberg-Witten theory and like coming from it in this regime of parameter space where I can really write this down. And so what I should think is now I should perhaps think of this theory I wrote down for you with all of this higher order stuff dropped as maybe like an effective Landau-Ginzburg-like description for the physics that I'm now going to describe for you. So think of it as at this point, because there are no strictly valid solutions in the reliable regime, I should maybe think of it as an inspired effective Lagrangian to do analysis.
Okay, thanks.
Thanks.
Does this have anything to do with the fact that sort of the phi equals 0 areas, like the strong coupling region, And like if you try to dualize it, does this m squared deformation just get completely messed up, or?
So I'm not sure if that's it. Indeed, like you say, phi goes to 0 this is the strong coupling region. This is the monopole point. And so the statement is I could have gotten something, I wanted something reliable, like very near to the monopole point or this multi-monopole point where all of these expressions are, you know, reliable in perturbation theory. And yeah, I don't have an understanding as to like the fact that we're close to this point being related to this issue. Yeah, I don't have an intuitive understanding of that.
Okay, cool.
Okay, thank you. Okay, so for the rest of, so now I'm going to describe for you the results of studying this effective theory. And so first I'll just describe the small m phase of this theory. So at small m, I'm just gonna I can focus on this term in the potential, it turns out. And so at small m, the minimum of this potential is a Coulomb phase vacuum, again, like maybe you'd expect from what I've told you so far, in which all of these HVEVs are set to 0. So in particular, the tadpole, so this is the tadpole here, and the tadpole sets the scale for where the minimum of this potential is. This is a very simple potential up here, and so I can solve for the VEVs of the vector multiplet scalars. They're set by this sign from the tadpole. In particular, I'll point out that, you know, as I just told you, even the smallest of these 5 VEVs is bigger than the mass of the lightest W boson. Like the smallest of these go like 1/n, which is still bigger than 1/n squared. So that's this fact I told you rearing itself up immediately. So so the second feature of this solution is that it's only stable below some upper limit of m, call it MCB for Coulomb branch. This scales like 1/n, which again is bigger than this cutoff, but okay. And so this is very much like the SU2 phase diagram I showed you, where there's some cutoff for the small m Coulomb phase. And the statement is that at larger m, there will be vacua with some of these HVEVs turned on that will take over, where I'll want to roll into some vacuum with some of these HVEVs turned on. And so the last comment is just the vacuum energy of this Coulomb phase vacuum. It scales like -n squared. And in particular, the comment I'll make is that you can also check the scaling of the vacuum energy near the origin of moduli space, and it also scales like this. So this matches the scaling at the origin of moduli space. So the lesson I would like to impart is that this we have qualitatively captured the features of the supersymmetric Coulomb phase vacuum at small m by studying this small m vacuum of this effective Lagrangian. So next, okay, I told you at larger m, this small m solution isn't even stable. What happens? And so now I'd like to tell you the results for some general properties of the phases at larger m. So first is what happens to CT. So, okay, here I've just written this potential for reference. You don't have to look at it if you don't want to. The first result is that every saddle point of this potential preserves CT, charge conjugation with time reversal. This in particular follows from the fact that all of the, you can check that all of the 5 VEVs have to be purely imaginary in a saddle point. And when these are purely imaginary, they're invariant under CT, which acts as I've shown here on this slide. And this is an argument that holds for all n greater than or equal to 2. Although for n equals 2, there's no charge conjugation So it would just be T for n equals 2. And so this is really interesting. We know by the Vafa-Witten theorem that CT has to be preserved in the phase that is actually realized by adjoint QCD, whatever that phase is. However, to be very clear, the Vafa-Witten theorem does not apply here to the deformed supersymmetric theory. Instead, we got out this result that CT will be preserved in the vacua of this theory just by an analysis, and in particular, it followed from the form of the tadpole in the SUSY-breaking deformation, which I'll remind you came from matching to Seiberg-Witten theory near the multi-monopole point. That's what's setting the fact that these 5Fs have to be purely imaginary. So that's the first interesting fact.
All right, Emily, can I ask really quickly?
Yes.
Why does Vafa-Witten theorem not apply to supersymmetric theory?
So basically because of the Yukawa interactions.
Oh, okay.
So I have these all these extra terms that I didn't even write down here, and so yeah.
All right, good, cool, thank you.
Okay, so interesting fact 2. Let's ask what happens to the chiral SU2R symmetry in vacua of this potential. So the feature, which is new for n greater than 2, which I hinted at the beginning of this talk, is that I need to consider the alignment of these HVEVs in SU2R space. And so I can check just by writing all the terms in the potential that depend on the relative alignment of these HVEVs, and then rewriting them in some nice SO3 invariant spin variables, that these terms that depend on the relative alignment exactly form a spin chain type potential, and so therefore their behavior is entirely dictated by the sign of these coefficients to the spin chain, and these coefficients are elements of the inverse matrix of effective couplings. And an interesting fact about our matrix of effective couplings is that these off-diagonal elements of the inverse are all negative as long as the cutoff is taken to not be too large. So therefore, this is a ferromagnetic spin chain. All of these relative spins want to align, and in fact, all of my H's want to align for a minimum of this potential. And so the result is that a global minimum of this potential with some H's non-zero, with some HVEVs turned on, preserves a U1R. It breaks SU2R to U1R. And so this is exactly the chiral symmetry breaking pattern I would have expected for the CP1 model. And again, I'll emphasize this is not required by Vafa-Witten in this softly broken supersymmetric theory, but it ensures consistency with it, which is an interesting result. And so the lesson is that this chiral symmetry breaking pattern of SU2R to U1R is a robust feature of this effective model. And in this case, it's really due to the non-trivial off-diagonal structure of the matrix of couplings. Third, what is the fate of charge conjugation? So I told you that CT was preserved for vacua of this potential. What about just C on its own? So I already told you how charge conjugation acts, and so the statement is that whether or not this is charge conjugation is spontaneously broken in some vacuum has to be checked for vacuum solutions. There's no general argument based on this potential. And so the result that we find is that there are metastable vacua that break charge conjugation, but actually all of the globally stable vacua preserve charge conjugation, and therefore preserve both charge conjugation and time reversal. So that's a fact of the dynamics. So here I was going to explain this to you in the test case of SU3. So this is a little technical. I'll try to go quickly. So for example, in SU3, I have two H's, two H's, H1 and H2. And so there's just one C conjugate pair of H's. And so a priori, I could have different branches. I could have both of them set to 0. This is the small m branch I already told you about. I could have one of them non-zero, or I could have both of them non-zero. And so a fact that you can show is that when both of them are non-zero, the stable vacua in such a case preserves C. So H1 equals H2. So then I can check by doing a stability analysis. Don't worry about the equations. I'm not going to do a careful analysis here, but if I do a stability analysis, I can check that actually the region of local stability of these equations is disconnected from the point where I can solve this equation for the HBEV. And so the fact that these two types of solutions are disconnected means that there's a first order phase transition between the two types of solutions. And furthermore, I can argue by just solving these equations, I'm showing some pictures here, that I will only get a solution that is locally stable in the region of local stability when M is bigger than some lower bound, call it M Higgs branch. And then I can get a solution to these equations where the HBEVs are non-zero. So I'll summarize for you the result for SU3. So this is another of these schematic diagrams of the phases. And so here I'm plotting schematically the vacuum energy of the different locally stable vacua, and this should remind you very much of the SU2 phase diagram that I showed you earlier. So at small m, I have this vacuum where both h's are set to 0, and it's this Coulomb phase vacuum I told you about. Then above some value of m, I can turn on a locally stable solution, which has both H1 and H2 non-zero and equal. So this is a C preserving solution. And there's going to be some transition point where the global minimum of my potential is this C preserving Higgs vacuum. Also, I haven't explained this to you, but if I do the analysis of that potential, there's actually also a metastable vacuum which breaks C, but is not the global minimum of the potential anywhere. Then there's this first order phase transition between the two types of vacua, and this large M vacuum with both H's turned on has these same features of the SU2 case that I explained to you. So the magnetic U1 squared is completely Higgsed by the two HBEVs, and I'm in a confining phase. The only massless degrees of freedom are the two Goldstone bosons, and these parameterize the CP1. And I'll just point out here that this is actually a non-trivial statement even for SU3. So if T had been diagonal, if these couplings had been diagonal and the U1s hadn't been coupled, there would have been more massless scalars, and I wouldn't have gotten the single CP1 out. But this is true for SU3 and for larger N, that because of these off-diagonal couplings, actually these other modes are lifted, and I'm only left with the two massless scalars. Okay, so for larger N, the statement is as follows. So there's a new feature for N greater than 3, which is that I have multiple charge conjugation symmetric pairs to deal with. So H1, Hn minus 1, H2, Hn minus 2, and so on. And so I have the possibility for even more transitions than this one transition that happened for both SU2 and SU3 as I dial up my SUSY-breaking parameter. And the result that we find is we find a sequence of phase transitions as C-symmetric pairs of these H's turn on one at a time. So at the first transition I'll explain this with a picture. So at the first transition to the first C-preserving vacuum where just two H's are turned on, this intuition that I explained to you from SU2 and SU3 completely holds. So here I'm showing you just an example from doing numerics for SU4. And so for SU4, I have two C conjugate types of solutions with H's turned on. I have H1 equals H3, and then I have this self-conjugate H2. So here I numerically solved for the stable minimum of this potential, and I'm zooming in on parameter space at this first transition point, where I transition from this red line is the vacuum energy of the Coulomb phase solution. And then here, this orange line is the vacuum energy of this solution with the first two H's turned on, H1 and H3. And so this is the, not schematic version of this schematic diagram that I've been showing you. And so the statement is that this first transition looks exactly like the SU3 transition, where I transition to the C-symmetric vacuum. It's a first order phase transition. There's also this metastable C-breaking vacuum hanging around, but it's not the global minimum. Then the statement is that at larger M, there's a transition to the vacuum with the next pair turned on. Here for SU4, it's just one more transition where I get a transition to all HVEVs turned on. So here in this picture, this is exactly the same picture I was just showing you, except this box is the picture I was showing you on the last slide. And I've just zoomed out to show you the next transition, which happens at a larger value of M, where all of these guys are turned on. And so this is numerics for SU4, but the general result that you can show analytically by expanding for large M with this potential is that this all H type vacuum that's C and T symmetric and has this, this nice symmetry breaking pattern is the global minimum of this potential at large M. And this is a statement that's exact for all N. So I'm almost done. I'm just going to end with a couple more details on this nice large M phase with all of the HVEVs turned on. So one thing I haven't told you about yet is that these HVEVs, they induce a UV Gaugino condensate. So the Gaugino condensate is related by supersymmetry to a descendant of this U2 Coulomb branch operator. This is the one that was trace phi squared at weak coupling. And I can expand this operator near the multi-monopole point, and I can expand it in particular in this large M vacuum with all the HVEVs turned on. I get some formula that depends on the HVEVs. I can plug in, this depends on the couplings and so on. And I can show that this Gaugino condensate scales like N. And so this is an interesting result because this is exactly the large N scaling of the Gaugino condensate that I would expect for a theory with adjoints. So again, this came entirely from very non-trivial scalings of all these vacua and these couplings in this abelian Higgs model, and it matches what I would expect for a theory of adjoints. So then the comment is, so here this is one of the phases of this Gaugino condensate because I'm just studying one of these multi-monopole points, and then there are N phases related by the Zn for the other multi-monopole points. Then I can compute the vacuum energy in this large M phase vacuum. Again, this depends on this how these couplings scale, and I get something that scales like minus N squared. And so again, the statement is that this check mark is because this is exactly this N scaling of the vacuum energy I expect in a theory with adjoints. And this came from non-trivial scalings of these guys. So the statement is that the detailed structure of these effective couplings was in this abelian Higgs model was really crucial to getting out these N scalings, which match what I would expect for adjoint QCD. So I'll end with just a little summary. So I described for you this series of phase transitions. There were intermediate phases with some HVEVs turned on, and then there is this nice phase, which was the global minimum at large M, which had all of them turned on. And I'll just summarize that this phase, we really had all of these properties we hoped it would have of this CP1 phase of adjoint QCD. So it was confining. All the U1s were Higgsed, and you can also show that the center symmetry is unbroken. It has the right chiral symmetry-breaking pattern. It has the right discrete symmetries. it has exactly the two massless scalars that parameterize the CP1, and those are the only massless modes. Everything else is heavy when I expand around that vacuum. And these properties came from detailed structure of this theory. It came from the structure of the effective couplings. It came from, some of these properties came from just studying the dynamics of this potential. Some came from the tadpole from matching to Seiberg-Witten theory, and so on. So just to summarize, I set out to interpolate between Seiberg-Witten theory and adjoint QCD by adding this soft supersymmetry-breaking mass deformation to the vector multiplet scalars. Then I motivated studying an effective Lagrangian that derives from Seiberg-Witten theory with this SUSY-breaking deformation and expanded near the multi-monopole points. Then with this semi-classical Lagrangian, I described a sequence of first-order phase transitions that interpolates between the small m Coulomb phase of the supersymmetric theory and a phase with the expected properties of the CP1 phase of adjoint QCD at large M. And in this large M phase, all the monopole fields condense, and this leads to confinement and chiral symmetry breaking, which I described for you. So that's it. Thank you for your attention.
Thank you very much. So I was wondering if there are any quick questions.
Oh, can I ask a question?
Please go ahead.
So I have two questions. One for the generic point in the moduli space, and a second one for the actual analysis with respect to the multi-monopole points. So the first question is that you argue that in the generic point in the moduli space, it is only scalar gets a mass, and then gauge remains to be, for example, massless, and that doesn't explain, for example, confinement and whatnot. I was wondering if this argument is valid only for small m, or it also works for the large m region.
Right. So the statement is that there I don't have these options for these phase transitions as I dial up m, because I don't have like extra like fields that could get a vev and break some of these symmetries. So it's possible that there is such a phase transition, but it's not accessible in a sense from the low energy description. So that's what's so nice about looking at this point in parameter space. All of this is completely accessible just from this effective description near with these fields near the monopole point.
I see. So okay. So the reason why I asked that question is because if I take a very generic point, I take my n equal to Seiberg-Witten, and then I add a very large deformation, I let it go, and then see if what are all the possible non-supersymmetric phases that I can expect. And it would have been satisfactory to show that for generic point, for large m deformation, like theory cannot never run into that phase, the Coulomb phase with the massless gauge, That would be satisfactory, but looks like we don't have a theoretical control to show that much.
That's right. We don't have the theoretical control. That's right.
Good. All right. Then the second question is about the multi-monopole analysis. So for small m region, you now still have power of a supersymmetry. Therefore, you just solve it exactly, and then just to try to add the deformation and understand what the IR phase is. So that's all good. Now for large m, on the other hand, of course, naively, then you are going from the SUSY theory to non-SUSY theory. But the good thing you can get in this case is that now this is in the weakly coupled region. That's why you use the semi-classical analysis, presumably.
That's right.
Why. Now, my puzzle is that there's these two pictures, right? So there's, okay, you can now do the semi-classical analysis. On the other hand, you lost your SUSY power. But then what is that extra bit left over below the M that allows you to learn about the IR phase still?
Okay, so maybe one comment that will help is that so I told you that doing the analysis elsewhere on the moduli space is uncontrolled at larger M, and in particular, like BPS states will become light at points such that happen before like these first transition points that I described for you in this phase diagram near the multi-monopole point. So there's not a contradiction between what the what I would get if I studied at some generic point versus what I get here. There's not a contradiction. However, like I'm doing something illegal by like letting myself extrapolate to large M near this point. Like strictly speaking, this is illegal. This could have given me nonsense. And because, you know, I'm dropping all of these things that, you know, could have been there, all of these corrections that could have been here. And so it's the kind of thing where if I had gotten nonsense, I would have said, okay, I got nonsense. Okay, but I didn't. I got this like very, very nice suggestive picture. And so that's why it's interesting to do this anyway.
Okay. I see. So it was that extrapolation that let you get non-trivial results. In other words, you did it in the small M region, and then you extrapolate to the large M region, and then learn about what are the possible low energy phases of that theory.
That's
and that kept, okay. Then in that sense, then it may. I'm not sure how you think about. So there is. So you show that there is a cascade duality or cascade confinement, right? Phase transition, multiple condensate.
Yes.
Am I supposed to believe that feature as a physical feature, or just intermediate step of the analysis, so that at the end of the day, I am supposed just to take the deepest IR?
So that's a good question. Like the question is basically like, imagine I were able to include more corrections and I were able to improve like how reliable this analysis is. Like, would that destroy all of these features?
Yes.
And so it probably wouldn't destroy the main features, like especially of like the small M phase and like these properties of the large M phase, especially since they match what we would have expected to get maybe. And maybe some things could change about these intermediate phase transitions. I think it's a bit unclear.
Okay.
And so I think this picture it's very suggestive, but I can't claim that this is the exact picture of phase transitions. It's just it's a very suggestive picture, but I can't claim it's exact. Yeah.
Right. I see. Thanks for the great talk.
Yeah, I mean, can I just also comment on what you just said, which is that I think one thing that you get out of this, which is not a priori obvious, is that the CP1 phase is continuously connected to adjoint QCD. Right? Like by getting to that Landau-Ginzburg theory, even though you do an uncontrolled extrapolation, it's still continuously connected.
That's right. That's right. It's continuously connected to this effective description.
Yep.
Yes.
But do we know that non-perturbatively, or like how do we like what's the level of reliability of that statement? That two phase or two descriptions are continuously connected.
Well, you know, if you try to guess an effective field theory for like to start with some kind of, like Emily said, like a inspired Landau-Ginzburg guess, it might just seem like bullshit if you made like kind of a random guess.
Okay.
Right. The point of the nice thing about the supersymmetric thing is that it gives the supersymmetric theory is it gives you a very inspired guess that you know is right, at least in the m = 0 limit.
Right.
So I don't know how to say whether it means we know something perturbatively, non-perturbatively, but it means that the guess is not made up. It's
right.
correct in the limit.
Right.
Right. And the guess it's really interesting that, I mean, this guess like is made out of just the degrees of freedom of Seiberg-Witten theory and produces these nice features. So yeah.
I had a question, Emily, about if you guys had looked at the confining strings at all.
Not really. Yeah, not really. I can't really say anything sensible yet about the strings.
Okay.
But that's something that we're hoping to look at next.
Yeah. Okay. Cool.
I want to suggest that we take a 5-minute break and then return for a more discussion. I have a bunch of questions myself. But first, I wanted to thank the speaker again. So.
Thanks, Emily.
Thank you.
Emily, that was a